excited to have Anna Halfpap here from University of Montana, and she's going to be talking to us about rational exponent questions for generalized extremal numbers.
Well, thank you for inviting me. I'm very excited to be here and giving this talk. I'm actually going to spend a fair amount of time just talking about rational exponents for ordinary Turan questions. So you don't have to think in the general world just yet. I think probably everyone here knows about like Turan's theorem, but just to very quickly remind you, I'm going to write ex of n and f for the max number of edges in an n vertex f free graph. And then remember there's a famous graph that we extremal graph theorists love called the Turan graph. And there are actually many of these. They all sort of look the same. So T sub kn is n vertex, complete k partite graph with classes as balanced as possible. Of course, depending on n and k, you might not be able to exactly sort them, but you can do your best. So, famous theorem, when we forbid, I'll say k plus 1, this extremal number is the number of edges in the k-partite Turan graph. Actually, you can say something slightly stronger, that the Turan graph is the unique optimizer here. So that's great, but those are only a few graphs. But fortunately, there's another famous theorem of Erdős-Simonovitz, which says that Turan's theorem is really pretty good for almost every graph you could have. So if you let f be your forbidden graph, and you say, let f be fixed with chromatic number, we'll say that that's k plus 1 also to match up here, then the extremal number ex and f is the number of edges in the k-partite Turan graph on n vertices, plus some error term, which is little o of n squared. So the Turan graph, I mean, we want to draw a picture. We've got these blobs here, all connected. We didn't explicitly compute how many edges are in there, but I mean, these are linear sized classes and we are complete between two classes. So if we have at least two classes, this is going to have order n squared edges. So what this says is that when our chromatic number is at least 3, then we asymptotically know any extremal number we want. You might be interested in figuring out what this error term is. That's not something that I'm particularly interested in, but I'm sure some people are. But notice there's one degenerate thing which could happen, which is if k plus 1 is equal to 2, then k is equal to 1. So the number of edges in the Turan graph on one part is 0, because we've just taken a big independent set. So as a consequence, ex and f, we know it's little o of n squared for any bipartite f. I'm guessing, hopefully, this is review for most people, maybe all people, but this is sort of the stage setting that we need to do. Of course, this seems mysterious in all the other chromatic numbers. We know really well what's happening. For bipartite graphs, it doesn't seem like we really know that much at all. And famously, it can be quite hard to find extremal numbers of bipartite graphs. There's still some small cases which are open. But instead of talking about single bipartite graphs, I'm going to talk more generally about the idea of what kind of functions could we even get there? Can we have something that is on the order of n? Can we have something that's on the order of n to the 3 halves? Well, this is a natural question, and so there's this famous conjecture called the rational exponents conjecture, which says for any r in the interval from 1 to 2 are rational, there exists f sub r, it would have to be bipartite, such that ex of n f sub r is theta of n to the r. We start at 1 here because sublinear things aren't really going to happen. I guess you could forbid something like a matching, and then you would not be able to take the trivial example of a matching of size n over 2, but ordinarily, at least we'll be able to get a linear number of edges. And so this really is the sensible range to think about. And now this conjecture is still open, actually. It's notoriously difficult. And for this reason, there is a weakening that was considered in the last decade, which says, okay, what if I don't need to have a single forbidden graph? What if instead I could say I have a maybe very big forbidden family, and I want to get the most edges possible with not having any member of my forbidden family present? And if we allow that weakening, so Bukh and Conlon, I think the paper was published in 2015, showed that for any rational r in the 1-2 interval, there exists a family, script f sub r, with ex of n script f sub r is theta of n to the r. And so the first thing that I want to do is talk in some detail about how this is proved, because the proof techniques here are interesting in their own right, and they'll also sort of inform how we approach the set of problems that I like to think about. Any questions so far?
Yes, what's the difference between the conjecture and the theorem?
This is for a single graph f, and here script f could be a set of many graphs. In general, you can't reduce forbidding a big family of graphs to forbidding a single element of the family.
I see. And who made the original conjecture?
It appeared in a paper of Erdős and Szymonovitz. I think sometimes it's also attributed to a couple of other people. Frankel wrote about it early, but I think Erdős-Szymonovitz is the typical conjecture. It's the same paper where there's the conjecture that only rational exponents are achievable.
Were the families they constructed like usually infinite or usually finite?
These are finite families. They might be very big, and the size of the family will depend upon exactly what R you're trying to pick. But basically, you start with a base graph and then make a bunch of constructions based on that, but for some like finite power. And so these will indeed be finite families. Any other questions? Okay, well then let's think about how we would go about this. We've already alluded to one thing that we would need. I'll say step 0 would be to choose a good candidate forbidden family. So a clever f sub r for whatever rational we want to achieve, which we would have some reason for thinking would achieve that exponent. Once we have this family, we're going to need, just to make sure everyone's awake, how do we certify that something is theta of n to the r? Well, we need to show that for n big enough, there's a couple constants, I'll say little c and big C, where little c n to the r is a lower bound, and big C n to the r is an upper bound. So we need a way to show that some n vertex graph with at least a little c times n to the r edges is script f sub r free. That'll show a lower bound. And 2, a way to show any n vertex graph on at least big C n to the r edges has a member of F. Okay, so I guess I should probably start by telling you step 0. None of the other things are really going to make sense if we don't know what we're forbidding. And so the forbidden families are going to be based on special trees, which are going to have a couple properties. They're going to be rooted trees, and they're going to be what we call root balanced. So we'll start with a rooted and balanced tree T sub AB, and these A and B are going to keep track of the number of unrooted vertices and the number of edges. So when I say rooted, I just mean that you can color in some vertices or draw them at the bottom of your picture or something, and you think of those as being in a separate root set. For example, my favorite Bukh-Conlon tree, because it's not trivial, but it's still small, is this guy. This is T5, 7. Now, the rooted density of a rooted graph is just the number of, I'll say parenthetically, unrooted edges. Here, of course, we have no edges in the root set, so this is all edges. It doesn't have to be that way. Divided by the number of unrooted vertices. T57, you can read off of its density very nicely here. We have 1, 2, 3, 4, 5 unrooted vertices, 7 edges. So this thing has density 7/5. Balanced basically means that if I go through and look at subsets of unrooted vertices and compute their rooted densities, so number of incident unrooted edges divided by the size of the subset, I would have to get a rooted density for that subset, which is at least as big as the rooted density for the whole thing. This is a technical assumption that we don't need to worry about too much, but it turns out that to do this random algebraic method, balancedness for your underlying rooted structure is an important assumption. Okay, so those are sort of the components of what the tree we start with has to have. Now you might be thinking, why am I talking about a tree? Of course, if I forbid this tree, we know the extremal number for trees is going to be linear, so that doesn't seem interesting. But we're not going to actually forbid this tree. We're going to pick a tree with a rooted density that corresponds to whatever rational I want in a specific way. And then f sub r will be the set of what we call k groves of the appropriate TAB. We say k groves because if we have a bunch of trees growing together, that sounds like a grove. So k grove, we're defining it now for actual trees, but you could have a k grove of any rooted graph. It's just a collection of copies of a rooted graph which agree on the root set. So their roots have to line up, and I have to be able to say, here in my K-grove, here's one subgraph that looks like my tree, and here's a second, and here's a third. I have to be able to find K of them. But I don't require that the vertices outside the root set behave in any particularly nice way. So for example, if I drew maybe just a 2-grove of this guy, I'll draw one copy that looks nice. And then a second copy, maybe I go up here, but then the second vertex in this, I don't want to have that be the second vertex. The second vertex could be this guy. And then the third vertex is this guy. And maybe the fourth vertex is over here, and the fifth vertex is also separate. You can see that I have these 2 copies here. There's been some weird vertex identifications, so it's not a tree anymore. It's not even 2 very clearly distinct copies of this tree, but somehow they've grown together. And the important thing is that they share this root set in that order.
And do you want still this thing to be bipartite?
So some of these might end up not being bipartite. I think you can make examples where you get odd cycles when you glue these things. So yeah, our forbidden family, it wouldn't necessarily be a problem if it has some non-bipartite graphs in it, right? If we just individually forbid non-bipartite graph, we're going to get way the wrong order of magnitude. But basically the idea is that we're going to want for the upper bound to say there is some root set where I can find a lot of copies of the tree that share the same root set, but I'm not going to be able to be any more precise about that, so I want to have every possible way that they could interact outside the root set. Clear enough? Okay, well then that transitions well into discussing the way that the upper bound works, and I gave you sort of the 10-second description, but let me say a few more words about it than that. So for the upper bound, I think this is fun because it's sort of silly that this is all you need to do. It should seem like the lower bound ends up being very technical, so the upper bound should be similarly hard, but we don't have to do anything fancy. We just get to do some greedy tree building. So how could you greedily build a tree? If you know that you have a graph of high minimum degree, or well, any known minimum degree, you can estimate the number of trees you have by just picking, say, a vertex to start with. And then you have at least the minimum degree number of choices for an edge. And then you say, where else do I need to glue an edge to build up a bigger subtree? And you have essentially the minimum degree number of choices for that second edge. You'll have to subtract a little bit at each step because you don't want to do something like build this much and then accidentally pick an edge that goes back there. That would be bad. No? But if you're building up a fixed tree, so we have a constant number of vertices, you're going to just be taking off like a constant number of choices at each step here. And when we're thinking of if we're thinking of something with a super constant minimum degree, then that would be fine for us. So in those cases, we could always build at least one of these. And actually, just sort of counting the number of ways to do this, we could get a decent function estimating how many we have. So the idea is, if I have a graph with at least this big C times n to the r edges, well, I can translate that into an average degree condition, right? Just using the handshaking lemma. So average degree here should be twice the number of edges, not 1/2. because I add up all my degrees and I get 2 times the number of edges, and I subtract 1 to average everything out. And then there's this folklore lemma that we all probably seen before, saying that you can get a subgraph of high minimum degree by just repeatedly removing vertices of low degree from something whose average degree you know. And what's the high minimum degree we can get? We can get at least half of the average degree in the original. So we then pass to a subgraph with minimum degree, at least the C and the R minus 1, and greedily build trees. So then we'll figure out the number of trees which we can greedily build in this way. And we'll divide that number by the total possible number of root sets. In this example, we have 3 vertices in the root, so there's n choose 3 ways to pick a root set. And the idea is that this average, then our favorite trick with averaging, we've got to have one root set that has at least the average number of these trees fixed there. And so in this way, you have to actually do the counting and analyze what you get, but it works out very nicely that this is just a constant, basically a function of C. And so as you choose C bigger, you'll be able to guarantee yourself that there's some place where you get a grove of as big constant size as you want. I guess I still haven't actually said what value of k we're going to choose here. That sort of pops out of something in the lower bound. But it won't matter for this step as long as I only demand a constant size grove. I will be able to get them as long as I choose this C big enough. Okay, well then, let's come over here and say a few words about the lower bound. This is the part of the talk that I'm kind of going to scamper lightly over because it's more technical, and if you're not into algebraic geometry, there might be a couple things that you just say, I don't want to see that theorem even stated. Do research on, you can either read a couple of papers or you can make a friend who already knows the technique. So, what is the basis here? It's using the random algebraic method. As you can guess, this is somehow probabilistic, but it also uses ideas from algebra. And the idea is that we've, all seen basic applications of looking in the random graph where we just decide if an edge is there with some probability p, each edge chosen independently of the others. But that method of generating a random graph gives a certain probability distribution on some features of the graph that you'd be interested in, size of the common neighborhood of some set of vertices, etc. And for some things, the standard random graph model is great, and for some things, the probability distribution that we get is not the right one to allow us to make good conclusions. And so this is a sort of alternate way that we could generate a random graph, and then we can use this alternate thing that we do and some theorems from algebraic geometry to sometimes make better conclusions than we could in the more standard probabilistic setting. So what's the construction? This is, you sort of vary a little bit how you construct it based on exactly what you're looking for, but in this case, we are going to do something that I think is a little simpler than sometimes you see, make a bipartite graph. This will be U and V, and we're going to think of these not just as vertices, but actually elements of a finite field of order q to the b in each set. And here, you know, you'd probably choose q to be really big. Primes and prime powers are dense, and so even though there's some number of vertices you can't explicitly represent this way, you're not losing too much. And we're going to choose independently at random polynomials p sub 1 through, I'll say f, so we don't think I'm talking about probabilities directly here, f sub 1 through f sub a, which are going to go from fq to the b cross fq to the b into just f sub q. I will need to have some kind of max degree condition since I want to be choosing from a finite set, but this you figure out, you know, you need it to be at least so big for certain things to work, and then you choose the smallest thing that will work. Okay, so why am I choosing these? Because as you can guess, I have two copies of fq to the b here, so I could put in one vertex from u and one vertex from v to each of these f's, and then I'm going to assign edges to exist when something happens specifically for u in u and v in v. uv is an edge if fi of uv equals 0 for all I. So just as a sanity check, what's the probability if I fix a u over here and a v over here, what's the probability that uv is an edge? Well, let's back up a little bit. What's the probability that f sub 1 of uv equals 0? 1 over q to the b. To the b? Well, remember, you're close, but remember they're going into f, not fq to the b, just fq. So 1 over q, and I think you see why. If you fix everything but the constant term, then putting in different constant terms shifts you around in f sub q, right? So for any polynomial, you can think of it as what are the coefficients on the things that are non-constant, and then there's exactly one choice of constant term that will land you at 0. So anything you put in, you're going to get 0 with probability 1 over q. I mean, you'd also get like 1 with probability 1 over q, anything you want. And then because these are chosen independently, we just multiply. So probability of one edge is q to the minus a, because there are a polynomials here. And then that tells you expected number of edges is q to the 2b minus a, because there are q to the 2b pairs here. And if you do a little bit of manipulation to more easily translate this into, okay, there's basically q to the b vertices here, 2 times q to the b. This gives you the right exponent. This gives you 2 minus a over b as the exponent of the number of vertices you have. And so if we're aiming at rational a over b, this is the right thing. But why do we want to go through all of this work when we have a perfectly good random graph model where we could figure out the expected number of edges much more easily? Well, because there's this nice result from this nice result from algebraic geometry that will let us say something cool about varieties. So if I fix root set R and let C be the copies of, I'll call my base tree, the Bukh-Conlon tree of the appropriate density I've chosen to make this work. We can think of C as really a difference of varieties. There's some degeneracy concerns that you have to take into consideration, especially if you have a big variety, and then there's some degeneracy variety that you define, and you want to take that out because it doesn't count true copies of some grove or of C. And then what we want to do is we want to figure out something about the size of C or expected size of C. Well, one thing that we could do is we'll actually, for the technical part of the theorem, not look at this, but a higher moment estimation. So the probability that C is bigger than some constant, little c, is the probability that the size of C raised to the s is bigger than or equal to little c to the s. By Markov's inequality, this is at most the expectation that the size of C to the s over little c to the s. You can figure out this is do a little work that I'm not going to show here to bound the top. But this isn't quite good enough. We don't want a constant here. So here's where the algebraic geometry comes in. It turns out that when you're looking at the difference of a couple varieties which have what we call bounded complexity, then, so there's a background theorem which says size of C is either at most some constant, which depends on how big this complexity of variety is, but nothing else, or it's at least Q over 2. So that's like a function of n, essentially. So what we can do here is if we make this little c equal to k plus 1, then the probability that we're at least k plus 1 is the probability that we're at least q over 2. And so that lets us then replace this denominator with a q over 2 to the s. And for the appropriate choice of s, we do that comparison. And we say the probability of getting a grove of size bigger than this k is little o of 1, which means we can do an alteration by taking off vertex from each of these bad root sets. And even though those vertices, they could have degree as big as order n, we're going to kill little o of n edges. And so the number of edges in our thing isn't going to go down by any appreciable amount. And so this is how we show that these groves don't exist. By the way, this c to the s, right, this is counting like s copies all laid together at the same root set. So that's where the grove comes in. Okay. So in the remaining 15 minutes, I'll pivot now. These are the ideas that go into the basic Bukh-Conlon theorem. And then, I guess, 9 months ago now, we asked, I just gotten to Illinois for a semester-long visit, and we we asked, what if we want exponents for generalized problems? So ex of n hf is the max number of copies of h in an n vertex f free graph. And I mean, natural generalization, if you replace h with an edge, this is the standard Turan number. Basic results from Turan theory also extend to the generalized setting. In particular, there is a degeneracy result, which is similar to the statement that your extremal number is little o of n squared if and only if you're bipartite. So, theorem, this is Conlon and Schickelman. Ex n hf is little o of n to the number of vertices in h if and only if f is contained in some blow up of h. And if not, then n to the number of vertices in h is the highest order you could possibly have. So you are, in fact, on that order. And so just like we look at the degeneracy theorem in the classical setting and we say, okay, what range of exponents could I have? We could choose any h here we want and say, well, there is some set of degenerate f's that I could pick. Can I pick an f, or given that we can't, we need families just for edges, I'm going to definitely need a family of f's to pick here. Can I pick a family to get whatever exponent? And the hope, of course, is that all this stuff I've gone through about how we prove the Bukh-Conlon theorem will be relevant. And in fact, some of it does just generalize. So the algebraic method stuff that I kind of glossed over, which might seem like the hard part, well, actually that's the easy part here, because if you understand that lower bound theorem, an analog of the lower bound theorem works here. You know, you say, here's my h, and it just says if you have a finite set of rooted graphs at densities at least d, then there are some size groves of those things that you forbid, and it gives you the lower bound corresponding to like the number of vertices in h minus the number of edges in h over d. So whatever, you can get a lower bound algebraic method thing to go forward fine. But then the stuff with the greedy building actually gets substantially harder. So we'll say, given random algebraic method not really being a problem, how to extend these ideas? Well, let's just focus on the example where h is a triangle. I want my construction that I base these groves on to be something that I could do like a greedy building argument for if I know that I have more than what I think this extremal number should be of triangles. Now, this doesn't say anything about how many edges I have. It says a little bit, but not directly. So I'm not going to want to have this be a tree anymore, because we greedily build trees by knowing we have some number of edges. And what do I know I have? I have some number of triangles. So that says that the base construction should really be what we call a triangle tree. Which loosely just means I've taken a bunch of triangles and glued them together in like a tree-like way. I don't have a cycle of triangles, although of course the thing contains cycles, in the sense that triangle is a cycle. And we're still going to need it to be balanced. So we have to say it has some subset of its vertices as a root set, and it has this balancedness condition given that rooting. And we're going to have to check that in fact it is greedily buildable in the right number of ways. And both of these things present challenges as even with triangles, but it gets harder and harder as this base H expands from being an edge to whatever graph you might want. So just to give you maybe a little bit of insight, here is, again, my favorite Bukh-Conlon tree. We know this is balanced. Maybe we can somehow exploit that fact to make some of these things a little bit easier to check. One thing I could do is just turn these edges all into triangles. Here's my root set. It's rooted, it has some density. You can actually check, yeah, this works. That's great news. Maybe it actually is as easy as just taking all these Bukh-Conlon trees at all these different densities and turning the edges into cliques. Well, no. Actually, this thing we can see quickly, it's only going to remain balanced as long as the density of the big construction is less than or equal to 2. Because if you look at one of these spike vertices, this is a single unrooted vertex with degree 2. So the local density at that vertex is 2. So this sort of trick only works in a low density regime. For higher density regimes, what we've ended up having to do is something like this. So I'll just tack on an extra edge everywhere. This is sort of how the Bukh-Conlon trees grow. To turn this into a triangle tree, now it would be of density too high to do this trick, so instead I'm going to do a series of identifications and place some edges inside the root set. I'm going to put an edge here. I'm going to identify this vertex. I'm going to identify this vertex. Leave this vertex alone. Identify, and edge. So when we have more edges to play with, you can play games like this and turn it into a triangle tree. Here we're gluing along edges sometimes, and sometimes along vertices. And things like that will work in general for higher densities. There's different rules based on exactly how many edges you have here. Okay, that's great. This you can prove is balanced. This you know is root balanced because you haven't changed the unrooted structure from a Bukh-Conlon tree. But you'll notice weird things are starting to happen. This root set now has edges in it. So we're going to have to think about those problems. We're going to have to maybe throw in some extra forbidden families to, for instance, be able to control the number of edges, which we would see in a construction, so we can well estimate the total number of root sets we're dividing by. If that is too big, we're not going to get the conclusion that we want. We're going to have to worry about, are these things greedily buildable? There's that folklore lemma, which says we can pass from a graph with high average degree to a graph with high minimum degree, but is it true that we can pass from a graph with lots of triangles generally to a graph where anytime I see a triangle, I have a lot of options for gluing along, say, an edge of a triangle? Well, things like that do work, but actually it's a little bit technical to prove that in every single density range that we need, we can glue in every single way that we need. So we've done triangles. We've proved that actually there's a triangle analog of the Bukh-Conlon theorem, that all exponents between 1 and 3 are achievable. We're just finishing up K4s. And for higher cliques, we don't know. It's sort of like there's this proliferation of you need different constructions at different density ranges, and so far it doesn't seem like there's just a way to do all cliques with one argument. The thing I want to leave you with in the last couple minutes, because it's short and it's satisfying, now that I've told you that we can get any rational exponent we want for K3 and K4, you might say, well, can I get any rational exponent I want for any random graph that I choose? That's the most that we could hope for, and I guess it'd be satisfying if it were true, but it's not. So the star on T leaves is not what we call rational. That is, it doesn't have all the degenerate rational exponents for any t bigger than 1. When t equals 1, this is an edge. We know that thing is rational. But if t is bigger than 1, we are not rational. And here's why. Consider Sn minus 1. So I have one really high degree vertex. These are all degree 1. If I want to find copies of St in here, well, this had better be my center, and then I have n choose t. So if I wanted to achieve an exponent smaller than t, I would have to say that this is not a graph I can have. But what would I forbid to forbid an n-vertex star? The only subgraphs which are of constant size, and we don't want to think about forbidding something like a star on root n vertices or something like that. The only subgraphs of constant size are just smaller stars, or I guess an independent set. So I would have to forbid some sk in order to avoid this construction, but that immediately says I have max degree bounded above by a constant, and so I only have a linear number of edges. So a star jumps from, you can have exponents of 1, and then you can't have any exponents until you get to t. And then for the range from t to t minus 1, we can use some techniques, make some constructions by basically gluing stars together in things that look like these Bukh-Conlon trees to conclude that exponents between t and t plus 1 are possible. So it's not just a finite set of exponents here, but there is this big gap. And so it's very open for which graphs we have the full palette of rational exponents. We are working right now on paths, and have just convinced ourselves that paths, you can't get exponents between 1 and 2 for, again, any path that's more than one edge. But, you know, things like a cycle, anything basically not complete, we don't know. So that's my time. Thanks everybody for your attention, and I'm happy to answer any questions.
Questions for Anna?
Anna, could you state your guys' triangle theorem for me? I mean, write it down. You said it out loud. I just would like to see it.
Yeah, I mean, it really just says for any rational r in the open interval from 1 to 3, there exists a family script f sub r with ex of n triangle f sub r is theta n to the r. And if you want to know exactly what that family f sub r is, they're all based on this grove idea. Depending on what sort of range your R falls into, it might just be the grove of one thing, like one of these triangle trees, or it might be like the grove of one of these things plus an appropriate grove from the edge case to make sure that you can have at most the right order of edges. And so it's a little, we don't actually in the paper write out explicitly what those families are in the main theorem statement, we sort of break them down.
I have a question. Maybe I'm confused, but so why does that mean that the max degree? Don't you forbid induced SKs?
No.
So you forbid just SKs? What, like?
So for when you forbid a graph, you just don't see that as a subgraph at all. It doesn't have to be an induced copy.
Wait, so are you counting SKs?
No, so I'm saying here, if we want to avoid this example, so if we're trying to achieve some exponent for ST, we say I want to have as many STs as I can without these forbidden graphs. Well, if none of the forbidden graphs live in this big star, then this big star is not forbidden. And so I have order n to the t copies of ST. So my exponent is not below t.
I see. So you are forbidding just any subgraphs?
Yeah.
Any copies of
Yes.
those?
So if I wanted to have an exponent below t, I would have to include something in my forbidden family, which says I can't have this construction, but the only subgraphs of this thing, induced or not, it is a star plus maybe some isolated vertices.
Yeah, but if you, like, if you wanted to only forbid induced SKs.
Answer in a short amount of time, but like, why can't you do the same thing but for irrational exponents?
Okay, so for it kind of gets swept under the rug, but remember, we draw, say, T5, 7 again. So it's not sort of arbitrary that we keep track of the density and how many edges and unrooted vertices we have. To achieve a specific rational exponent, you choose a base structure to work on that has an associated density. And these densities are always going to be rational numbers, because you just take, in the edge case, number of edges and divide by number of unrooted vertices. And really, in any situation with a finite size graph, you're only going to get a rational density. So we get rational exponents out of this because it turns out that you can, for any rational density that you need, make up one of these things, but you can't make up one that has an irrational density. And actually, I think I don't know of any. I know for hypergraphs, irrational exponents occur. I don't know if the rational, or not this rational exponent conjecture, but the other one that says that all graphs have a Turan number, which is like leading exponent rational. I don't know if there's a counterexample to that that's been shown. I don't think so. So, I mean, in some sense, the reason that we focus on the rational exponent conjecture rather than say, oh, can I also get all irrational exponents, is because that's a separate big conjecture, is whether irrational exponents are even possible. And I think people think still no for two graphs. Again, for like hypergraphs, and something like this has been done by somebody else for hypergraphs, irrational exponents can happen, and so you could ask more generally in that setting.
Okay, let's thank Anna again.